Chapter 7 is about bottlenecks, the external limits that constrain your application's performance, many of which exist completely outside your code. Let's start with the host, the server your application runs on. There are two types of limits on the host: hardware and software. Hardware limits are the most visible. Your application might consume all available memory and start hitting disk for swap, or it might saturate CPU. Adding more memory by upgrading your host, whether physical or virtual, is the obvious solution. But for Node.js applications, there's a layer above hardware, a software memory limit imposed by V8. By default, V8 allows about 1 GB of old space on a 64-bit machine. Even if your server has 16 GB of RAM, your Node process will crash at 1 GB unless you explicitly raise the limit. You do that with the max_old_space_size flag. For example, node max_old_space_size 4000 application.js runs your app with a 4 GB limit. But the book makes an important point: if you find yourself doing this, you've probably chosen a design pattern unsuitable for the task. The real solution is to split your application into smaller services. Beyond memory, the operating system imposes its own soft limits on processes, and the defaults are designed for moderate usage, not high-performance servers. The most critical one for Node.js is the maximum number of open file descriptors. A socket is a file descriptor. On Linux, the default limit is 1024, meaning at most around 1000 concurrent clients. You check and change these limits with ulimit a. You can also tune kernel parameters using the sysctl command. Key parameters include vm.swappiness, how aggressively the OS uses swap, vm.overcommit_ratio, and many others. Services like MySQL also have hidden performance traps. For example, inodb_flush_log_at_trx_commit defaults to 1, which means every transaction flushes to disk. At 100 transactions per second, that's 100 disk flushes per second. Setting it to 2 reduces this to at most 1 flush per second, dramatically improving write throughput at the cost of ACID compliance. Let's go deeper on the specific settings that matter for a production Node.js server. The ulimit command controls per process resource limits at the operating system level. Running ulimit on a Linux system shows all the current limits. The ones most relevant to Node.js are open files, n, which defaults to 1024. This is the single most important limit to raise for a high concurrency server. Every socket, file handle, and pipe counts against this. You should raise it to at least 65535 for a production server, and many operators go higher. You also have max user processes, U, which limits how many processes or threads can be created. The stack size, S, defaults to 8192 kilobytes. This matters less for Node.js since it uses its own V8 stack, but it can affect native modules. Beyond process level limits, the kernel itself has parameters you can inspect and modify with the sysctl command. Running sysctl gives you hundreds of settings. The virtual memory group, the VM** parameters, controls memory behavior, how aggressively the kernel reclaims memory for swap, how it handles out-of-memory situations, and how it manages page cache. For a high-load Node.js server, you typically want to reduce swappiness so the OS doesn't waste time swapping to disk when it could hold data in memory. Service configuration is equally important. A poorly configured database server can become the bottleneck even when Node.js itself is performing fine. Always check that services like MySQL, Redis, or Nginx are configured for your workload, not the defaults. When you don't control the production environment, for example on a shared hosting provider or a managed cloud service, you can't change these limits. This is where you reach the real ceiling. Knowing what the limits are helps you design around them rather than discovering them during a production incident.